Okay, so we're now on another application of first order differential equation, and this is about Newton's law of cooling. So the Newton's law of cooling states that the rate of change of the temperature of a body, so placed in a medium of constant temperature, so is said to be proportional to the difference between the temperature of the body and the medium. Okay, so the change in the temperature so depends on the difference between the temperature of the body and that of its medium. So mathematically speaking, so the differential equation involving, okay, so for this application would be d of t, so over dt, okay, so which is equals to k times t minus t sub m. And we can solve the differential equation through the methods for separable equation, so yielding to our working equation, so involving the change in temperature, so to be t minus t sub m is equals to c e raised to kt. And take note that t here so corresponds to the temperature of the body or the temperature of the object that we are referring to, and t sub m so corresponds to the constant temperature of the medium or the environment where a certain body is placed into. Okay, so there are various applications for Newton's law of cooling. So let's just say, so we want to determine how a certain object changes its temperature, so depending on its environment. But we have to take note here that the limit of the temperature of a certain environment so could only goes up to a maximum temperature of the medium. So let's say we have cookies. Okay, so we want to bake on or inside an oven. So the maximum temperature so that can be attained by the cookies would just be the temperature set on the oven. So the cookies cannot go beyond, okay, so beyond the temperature of the oven. And similarly, so if let's say we want to place let's say water inside a refrigerator, so the lowest temperature so that can be attained by water inside the refrigerator would be simply the temperature of inside the refrigerator. So it could not go beyond, okay, so or be even below the temperature set on the refrigerator. So Newton's law of cooling is also used in murder cases. Okay, so let's say we want to determine so when was the time a certain crime was committed. So it's because it talks about a certain object or a certain body whose temperature changes. Okay, so when a person is alive, so the temperature or there is a specific temperature of the body. So when a person is alive, however, the body temperature decreases. Okay, so once the body, okay, or once a person dies. So that is, or those are just some examples. Okay, so when we can use Newton's law of cooling, as long as there is a change on the temperature, so in relation to a constant temperature of the medium, so then we can use the Newton's law of cooling. So Newton's law of cooling, in solving problems so pertaining to Newton's law of cooling, so we always have to distinguish so which is the body that we are talking about and which or what is the environment. Okay, because there are cases that although of course that the temperature of the medium is constant, but then the initial values for the temperature of the body which changes is also constant. Okay, so that's why there is a possibility that the two temperature will interchange with each other. So that is why we have to take note the difference between T and T sub m. So T, so that is the body that we are talking about, and then T sub m, where is that body subjected into. Okay, so the T is the medium, the temperature of the medium. Okay, so to better understand that, so let's proceed with our first example. So that is the temperature of a metal is 20 degrees Celsius. So it is submerged in a large body of liquid of temperature 5 degrees Celsius. So after a minute, the temperature of the metal dropped down to 10 degrees Celsius. When will the metal's temperature be 6 degrees Celsius? And after 30 seconds, so what will be the temperature of the given metal? So we have to take note here So what is considered to be the body? Okay, so in here, so we have a metal. Okay, so a metal, so which is submerged into a large body of liquid. So therefore here, so the metal so will correspond as the body, okay, that we are referring to, and then so the environment or where or the medium, so where the body was submerged would be on the body of liquid. Okay, so the liquid, okay, so this one would correspond as our medium. So from there, so we can now get that for our given, so we can see here that the temperature of metal is 20 degrees Celsius. That is initially. Okay? So T here, so would correspond to the body. So initially when time is 0, the temperature of the body or the metal is 20 degrees Celsius. And then it is submerged to a large body of liquid. So since the liquid here corresponds to the medium, so its temperature is 5 degrees Celsius. So therefore, our T sub M then will be 5 degrees Celsius. So initially, that would be 20 degrees Celsius. And then the medium's temperature is 5 degrees Celsius. Okay, so take note here. The temperature of the body or the medium is 5 degrees Celsius, so which is lower than that of the metal, so which is 20 degrees Celsius. So once we submerge the metal into the liquid, okay, what would happen here is there will be a decrease in the temperature. Okay, so there will be a decrease in the temperature. So from 20 degrees Celsius, after a certain period of time, okay, so it will drop down or it will decrease. Okay, so from 20 degrees Celsius, and after an infinite time, okay, so after a very, very, very long time, so that is the time that the body could reach or could assume the temperature of the environment, okay, or the temperature of the medium, which is 5 degrees Celsius. But again, of course, take note that Newton's law of cooling is governed by the law of conservation energy. So therefore, we can only lose as much as heat as much as up to 5 degrees Celsius only. Okay, so we cannot go beyond or below 5 degrees Celsius because that is already the minimum temperature. Okay, so that our body can reach or that the metal can reach. So for our other given, so it says that after a minute, okay, so after 1 minute, so the 20 degrees Celsius so drops down to 10 degrees Celsius. Okay. And then so for the requirement, so when will the metal's temperature be 6 degrees Celsius? Okay, so what would be the time? Okay, so when the temperature is 6 degrees Celsius. So we are to find what is T. And for the second one, so after 30 seconds, so what will be the temperature of the metal? Again, so we have to be consistent on our units. So this is a minute, and then this time, so we are asked for 30 seconds. So since we use minute, so as our official unit for time, so therefore we convert the 30 seconds into minutes. So that would make it, what will be the temperature? So when it is 0.5 or half a minute, okay, so that's equivalent to 30 seconds. So for our solution, so of course we always start with our working equation, that is T minus T sub M is equals to CE KT. And then we substitute our initial values, that is when time is equals to 0. So we use this one. So the temperature is said to be 20 degrees Celsius. So we substitute. So T is 20, our T sub M, so which is constant, and that is 5 degrees Celsius. So 5 is equals to CEK times 0. E raised to 0 is 1, so therefore C is equivalent to 20 minus 5, so which is 15. So thus we can substitute. Okay, so our equation or our new equation now, so would be T, then T sub M is constant, so which is 5, is is equals to C, which is 15 now, then e raised to kt. So we need another value or initial value. So in this case, that is when t is equals to 1. So we have a new temperature, so which is 10 degrees Celsius. So which is 10. So to find for the value of k. So that will become 10 minus 5 is equals to 15 e raised to k times 1. So 10 minus 5 is 5. And then I could bring down 15. So to make it e raised to k. Then so ln, so 5 over 15 is 1/3. Is equals to ln e raised to k. So we can now have k to be equivalent to ln of 1/3. So thus, our working equation now finally would be t minus 5 is equals to 15 e raised to t ln of 1/3. So t minus 5 is equals to 15 e raised to t ln 1/3. So we can now proceed with our first requirement. So that is, so what would be the time for us to reach 6 degrees Celsius? So as you can see here, so 6 degrees Celsius is below 10 degrees. And 10 degrees would be after a minute. So therefore, for the temperature to drop down even further to 6 degrees Celsius, so it should drop down to, or we could have more time, okay, so for that to happen. So that is when the temperature is 6. So what will be that time? That is 6 minus 5 is equals to 15 e raised to t ln of 1/3. So 6 minus 5 is 1. So we divide 15. So that would make it, and then take the ln of both sides. So I'll just have ln e raised to t ln of 1/3. Okay, so 6 minus 5 is 1, then divide it with 15. Then we take ln of both sides, so giving us t, so to be equal to ln of 1 over 15. So divide it with ln of 1/3. And giving us the time, so ln of 1 over 15, so divided with ln of 1/3, so to be equal to 2.47 minutes. So it would take more than a couple of minutes. Okay, so for the temperature, so to drop down to 6 degrees Celsius. So the next question is, after 30 seconds, so what will be the temperature of the metal? So in this case, so since that is 30 seconds, so 30 seconds is in between 0 and 1 minute. So therefore, we are expecting that our temperature so would range between 20 degrees Celsius up to 10 degrees Celsius only. Okay. So in this case, so we just simply write that when time is 0.5, so what will be the temperature? That is t minus 5 is equals to 15 e raised to 0.5 ln of 1/3. So the temperature then, so 15 e raised to 0.5 ln 1/3, and then plus 5. Okay, so we add 5 after, so that would make it 13.66. So 13.66 degree Celsius. So that is for the temperature. Okay, so which is in between 10 to 20 degrees Celsius as expected. Okay, so that's how the Newton's law of cooling works. Okay, so it's similar with growth and decay. So the only difference is the difference of the two temperatures, the temperature of the body and the temperature of the medium. So let's have our second example. So for the second example, so a metal sphere, so when suspended in a constant temperature and closure, so cools from 80 degrees Celsius to 70 degrees Celsius in 5 minutes. and to 62 degrees Celsius in the next 5 minutes. So calculate the temperature of the enclosure. So initially, so the temperature of the sphere, okay, so a sphere here is considered to be, okay, so a sphere, so it's considered to be the body, and then it is suspended in a constant temperature enclosure. So enclosure, so would correspond to the medium. So the sphere, so cools from 80 degrees Celsius. So that means initially, so when time is 0, so the temperature of the sphere is 80 degrees Celsius. And then it drops down to 70 degrees Celsius in 5 minutes. So that means after 5 minutes, so from 80, so it becomes 70 degrees Celsius. And then it further drop down to 62 degrees Celsius in next 5 minutes. And so in another 5 minutes, so that is 5 plus 5, so that would be 10 minutes. It further dropped to 62 degrees Celsius. So we are to calculate the temperature of the enclosure. So in short, so what was required would be the T sub m, or the temperature of the medium itself. So for our solution, so we start with our formula, that is T minus T sub m is equals to CE KT. That is when time is equals to 0, okay, so the temperature is 80 degrees Celsius. So that makes it, so 80, so minus T sub m is unknown, so we do not know it. Then C e raised to k, so time is 0. So this one is 0, or sorry, it's 1. So therefore C is just simply 80 minus T sub m. So rewriting our equation, I now have, so T minus T sub m is equals to RC. It's 80 minus T sub m, then e raised to KT. Okay, so that's our new working equation. But then, so we have two givens unknown, or two initial values, I mean. So when T is 5, the time is 5, so the temperature is 70. The other one is when T is 10, so the temperature is 62. So we substitute them both, okay, so to our equation, okay, so for us to find the value of T sub m. Okay, so since those are time and temperature, so there are two variables given there then or left, that is the T sub m and the K. Okay, so we substitute it first. So when T is 5, so T is 70. So 70 minus T sub m is equals to 80 minus T sub m, then e raised to, our T is 5. Okay, so T is 5, so that make it 5K. And so I can transpose the 80 minus Tm, okay, so to the left hand side, so by cross multiplying it, so giving us e raised to 5K. So that is our working equation 1. For the second one, so we substitute when T is 10, so the temperature is 62. So 62 minus T sub m equals to 80 minus T sub m, e raised to, our T this time it's 10, so that makes it 10K. And similar to what we did, so it would make it 62 minus T sub m all over 80 minus T sub m is equals to e raised to 10K. So supposedly we have our second working equation, but then there are two variables involved here, the T sub m and the K. So since we want T sub m, okay, so we want T sub m, so we need to eliminate, or we need to equate both sides by K. Okay, so but then e raised to 5K is almost the same. Okay, so with e raised to 10k. So I can make this one e raised to 10, 62 minus t sub m and 80 minus t sub m. So this is the same as e raised to 5k and then raise it to 2. Right? So e raised to 5k raised to 2 because 2 times 5k, that would be 10k. And then, so if I want to remove the square there, so I can take the square root of both sides. So leaving us that the square root of 62 minus t sub m all over 80 minus t sub m is the same as e raised to 5k. Right? So e raised to 5k is the same as the square root of 62 minus t sub m all over 80 minus t sub m. And thus we can equate. Okay, so we equate both e raised to 5k. So that will give us, so 70 minus t sub m all over 80 minus t sub m is equals to the square root of 62 minus t sub m all over 80 minus t sub m. So this is our equation now. So there's a square root involved, a radical involved. So I'm going to square both sides. So that would give us, so 70 minus t sub m raised to 2 and divide it with 80 minus t sub m raised to 2. Okay, so we distribute, so both to the numerator, or we expand both the numerator and the denominator. And then this one, so the radicals will be removed, so leaving us to have 62 minus t sub m all over 80 minus t sub m. And thus, if I am going to cross multiply this, so that would make it 70 minus t sub m raised to 2. Then I could have 62 minus t sub m. So this one will move to the right. So 80 minus t sub m squared all over 80 minus t sub m. Okay. So as you can see here, so these two are the same. So the only difference is, so there's still an exponent of 1. So for the numerator. And thus we can expand this. So 70 minus tm raised to 2. So binomial expansion, so 70 squared is the same as 4,900. And minus 2 times 70 is minus 140. So t sub m, and then plus t sub m squared. And for the right hand side, so we multiply. So FOIL method, 62 times 80, that is 4,960. And I could have the negative 80 tm and negative 62 tm. So negative 80 minus 62, that is negative 142 t sub m. And then plus t sub m squared. So adding tm squared on both sides, so this one would just cancel out. And then I'm going to move the negative 142, so it will become 142 t sub m, so minus 140 t sub m. And then 4960, then transpose minus 49. So this would become 2 t sub m, and this is 60. So t sub m, so would be equivalent to 30 degrees Celsius. So that will be the temperature of the environment, okay, or the medium, so which is 30 degrees Celsius. And let's proceed with a third example. Okay. So third example is a murder case. And we want to determine, so when did or what time did the murder occur? So in a murder investigation, so a corpse was found by a detective at exactly 8 p.m. Okay. So the detectives arrive at 8 p.m. and right there, the detective measured the body temperature and found it to be 70 degrees Fahrenheit. So for our given, so initially, okay, so I'm referring to the time 0. So the body of the corpse was measured so to be 70 degree Fahrenheit. So take note that this one happens at 8 p.m. Okay, so that temperature was logged at 8 p.m. So 70 degrees Fahrenheit. So for the temperature of the corpse. So 2 hours later, the detective measured the body temperature again and found it to be 60 degrees Fahrenheit. Okay? So from the moment the body was found, so the temperature even drops down to 60 degree Fahrenheit. So that is after 2 hours. So after 2 hours, the temperature, so from 70, so it becomes 60 degree Fahrenheit. So that is at 10 p.m. Okay, so at 10 p.m., so the temperature of the body is 60 degrees Fahrenheit. If the room temperature 50 degrees, if the room temperature is 50 degrees Fahrenheit, so that is T sub m, which is 50 degrees Fahrenheit, and assuming that the body temperature of the person before death was 98.6 degrees Fahrenheit, so what time did the murder occur? So for our requirement, so we need to find what's the time when the temperature is 98.6 degrees Fahrenheit. So initially, again, so when time is 0, the temperature is 70. So we substitute. So 70, our Tm is 50, is equals to C E K times 0. So this will be 1. So therefore C is 20. So that would make it, so T, our Tm is 50, so C is 20, e raised to K times T. Then for our second initial value, so that is after 2 hours, so the temperature this time is 60 degrees Fahrenheit. So when T is 2, so the temperature is 60. So we substitute. So 60 minus 50 is equals to 20, e raised to K, our T is 2. So this is 10 all over 20 is equals to e raised to 2K. So ln of 1/2 then is equals to ln e of 2K. So K then is equivalent to ln of 1/2 divided with 2. So our final working equation would be T minus 50 is equals to 20 e raised to T ln of 1/2 all over 2. So T minus 50, okay. So now we can solve for so we can solve for the time. Okay, so that is when the temperature initially is 98.6. Right, 98.6. So what would be the time? So of course, so since T, our reference is, or the 0 hour is considered to be the 8 p.m. And since the temperature here, it's 98.6. So which is higher as compared to 70 degrees Fahrenheit. So therefore, we are expecting that the time that we will be getting here will be negative. Okay, so because it's way before our 0 reference time. Okay? So the time that we will get here is negative. So therefore, we're going to subtract it. Okay, so from that only means that we need to subtract it from 8 p.m. Okay, so to find the exact time. So to find for t, so we substitute. So 98.6 minus 50 is equals to 20 e raised to t ln of 1/2 all over 2. And this would be 48.6 divided with 20 equals to e, so t ln of 1/2 all over 2. So take ln of both sides. So giving us to have t, so to be equivalent to 2 ln of 48.6 all over 20 divided with ln of 1/2. So finally, so we will get a time there, so which is equivalent to negative 2.5619. So that's hours. So that means 2.5619 earlier, 2.5619 hours earlier than 8 p.m. So since our reference time is 8 p.m., so to find exact time, so that would be, so 8 p.m., then we subtract the 2.5619, so which is equivalent to 5.4381. But then, so the exact time for this, again, so using our calculator, so we need to find the negative key, and then there's another key there, so would correspond to change to the degree, minutes, and seconds. So pressing that button on your calculator, so it will transform the 5.4381 so into 5:26 and 17.11 p.m. So this is the exact time of the murder. Okay, so it took around 5:26 and 17.11 seconds p.m. Okay, so 5:26 p.m. And that is how our murder cases, okay, so determine the approximate time of when the crime was committed. Okay, so we can do that one mathematically, so through differential equations. And last example, so we have a certain body, so which is moved from one medium to another medium. So what happens? Example, at a certain time, so a thermometer reading 70 degrees Fahrenheit. Okay, so we have the body. So in this case, so the body will be the thermometer. And then it is taken outdoors where the temperature is 15 degree centigrade. So outdoors here, so correspond to our first medium. Medium number 1, so that is outdoors. So we have a thermometer. So initially it has a reading of 70 degrees Fahrenheit. And then it is taken out or taken outdoors where the temperature there is 15 degrees Fahrenheit. So 5 minutes later, the thermometer reading is 45 degrees Fahrenheit. So after another 5 minutes, the thermometer is taken back indoors. So this time, so it is taken back indoors, so which corresponds to our medium number 2. So we have two mediums involved here. So therefore, we have to write our given, so according to the medium. So for our given, so initially, so for medium 1, although our body is just the same, okay, so the temperature of the body, but then I would write it as T1, the temperature of the body outdoors. So that means, so initially the temperature of the thermometer is 70 degrees Celsius or degree Fahrenheit, I mean. And then the temperature outdoor, Okay, so where the temperature is 15 degrees Fahrenheit, so that means our Tm1 is equals to 15 degrees Fahrenheit. So 5 minutes later, the temperature reading is 45 degrees Fahrenheit. So that means after 5 minutes, so from indoor to outdoor, so it drops down to from 70 to 45 degrees Fahrenheit. And then after another 10 minutes, so the thermometer is taken back indoors. So that means after another 5 minutes. Okay, so after another 5 minutes, that is 5 plus 5, so I'll have 10. Okay, so meaning 10 minutes after it was taken outdoor, okay, so it was returned indoors. But what would be the temperature after 10 minutes? I do not know. Okay, so the temperature before, okay, so right before it will be taken indoor, so we do not know. So this is for the first medium. So for the second medium, okay, so when it was taken back indoor, okay, so indoor, that means initially okay, so when it was taken back indoor, so what would be the temperature? Actually, when it was taken back indoor, the temperature is the temperature after 10 minutes, right? Because after 10 minutes, it was taken back indoor. So therefore, the initial temperature for the medium number 2, okay, or the second medium, so that is T sub 1 of 10. Okay. And then, the temperature there is fixed to be 70 degrees Fahrenheit. Okay, so that means indoor, the temperature is 70 degrees Fahrenheit. The question now is, so what's the thermometer reading 10 minutes after it was brought back indoors? Okay, so for our requirement, that would be, so what's the thermometer reading? So what's the temperature after 10 minutes that it was taken back indoor? So our reference this time, when it was taken back indoor. For the second one, so when will the reading to the nearest degree returns to its original reading of 70 degrees Fahrenheit? As you can see here, it started with 70 degrees Fahrenheit. But then, so when will the reading to the nearest degree? Okay, so when will be the time? By the way, this is T sub 2. So when will be that time when approximately, so the temperature, so nearest the degree, okay, so which is 70, so the nearest degree would be 69 degrees Fahrenheit. Okay, so we're gonna write 70. Okay, so it will yield to an undefined answer. So our answer here is close to 70. So when will it be close to 70? So let's say it's after 69, or when the temperature is 69 degrees Fahrenheit. Okay, so for our solution then, so we start with, again, so T1 minus Tm1 is equals to C1 e raised to KT1. As you can see here, so I had written, or I wrote a subscript, okay, so for the body of the temperature indoor, the temperature of the medium, T1 corresponds to the temperature of the body outdoor. So Tm1 corresponds to the temperature of the outdoor medium. Then C1 so would be the arbitrary constant, and then T1 would be the time. But then for K, so I did not use any subscript. It's because when we are talking about the proportionality constant, so in problems involving Newton's law of cooling, so K is somehow inherent, okay, so with the system. Okay, so K is inherent with the combination of the environment and the body. So therefore, K here is constant. Okay, so regardless, so whether it is indoor or it is outdoor, so the K will maintain its value. It's different for C. Okay, so C, so depends on the time. Okay, so it depends on the temperature of the body and the medium as well. Okay, so for problems so involving, okay, so for problems involving a change in the medium, so take note that K is constant. Okay, so the value of the proportionality K doesn't change. Okay, so we substitute. So initially, so we start, so when T is 0, so T1, or when T1 is 0, so T1 is 70. So we substitute, so T1 is 70, so Tm1 is 15. So C1 e raised to K, T1 is 0. So this makes it 0, so therefore C1 so will be 55. And we substitute, so T1 then minus 15 will be equal to 55 e raised to KT1. And then, so when T is 5, when T1 is 5, so the temperature so drops down to 45. So that makes it, so 45 minus 15 is equals to 55, then e raised to K times 5. So 45 is 30 all over 55 is equals to e raised to 5K. So we take ln of both sides, so therefore K then will be ln of, so 30 over 55 is the same as 6 over 11. Divide it with 5. And then our T1 then will be, so T1, so minus 15 will be equal to 55 e raised to, so T1, so ln 6 over 11, so divide it with 5. So that will become our working equation. So now, so when, so we solve for the time, okay, or the temperature after 10 minutes. So before or right after, okay, so it will be returned back indoor. So when T is 10, so what is T1? So T1, so go, so transpose 15, so make it 15 plus 55 e raised to T1, so which is 10 ln of 6 over 11 divided with 5. So giving us for T1 to be equivalent to, so 55 or 15 plus 55 e raised to 2 ln 6 over 11. That is approximately equal to 31.36 degree Fahrenheit. So 31.36 degree Fahrenheit. So I am using continuous calculator or calculation. So therefore, although I had written 31.36 degrees Fahrenheit, so I store the entire value in my calculator. Okay? So as to okay, so lessen the error for rounding off. Okay, so now that we have our T1, so therefore here it follows that, so since T1 is approximately equal to 31.36 degrees Fahrenheit, so it follows that when the time is 0, okay, that is when the time it was taken back, so the temperature is 31.36 degrees Fahrenheit as well. So since we have now T is equals to 0 and the temperature is 31.36 degrees Fahrenheit, so we can now compute for the new temperature or the new value of C. So in this case, I would have T sub 2, okay, so minus Tm2, is equals to CE or C2 EK T2. So our temperature is 31.36, Tm2 is 70, then we have C2 e raised to K. Initially that would be 0 for the time. So therefore C2 is 31.36 minus 70. So giving us to have T2 minus T sub M2 is equals to 31.36 minus 70 e raised to our, as I mentioned, K does not change. So I'm going to use the same value for K. So which is ln 6 over 11 over 5. So ln 6 over 11 over 5. So our Tm2 is constant, so which is 70. So we have our second working equation. So that is, so for our first requirement, that is what would be the temperature. So what is T2 when time is 10 minutes? So that is T2 is equals to, so 70 plus, so 31.36 minus 70 e raised to 10 ln of 6 over 11 divided with 5. So that makes it 58.5. So 58.5 degrees Fahrenheit. Degree Fahrenheit. And for the second requirement, so when will be the time so that the temperature is approximately 69? So we'll have then 69, so minus 70 is equals to, so 31.36 minus 70 e raised to T2, so ln of 6 over 11 divided with 5. So 69 minus 70, which is negative 1, over 31.36 minus 70 is equal to e raised to T2, so ln of 6 over 11 divided with 5. So take ln of both sides. So T2 then, so will be 5 ln of, that's negative 1 all over 31.36 minus 70 divided with ln of 6 over 11. So the time then, so will be, it would take 30.14 minutes or half an hour approximately. So for it to return approximately close to 70 degrees or 70 degree Fahrenheit. So which is the original temperature of the thermometer. And that is Newton's law of cooling. Good day and God bless.